Hi everybody, so asymmetric capacitors are really interesting things. There's actually been a couple of things. One thing is in the supercapacitor sense, where you have a layer of carbon and a layer of some material like manganese dioxide, for example, and the two anode and cathode plates are different and create an asymmetric capacitor, but that's not what I mean. An asymmetric capacitor in this sense has identical plates, two aluminium plates like in a normal capacitor, but one is very much bigger than the other. Now if you put a high voltage on a capacitor like that, you get a very curious effect. You get an asymmetric field. Now there have been what's called ion wind lifters, and that's not what we're talking about. An ion wind lifter will strip away electrons, leaving ions that are then streamed to the other plate, and it's literally a wind that creates a thrust, and that's not what we mean. When we're talking about asymmetric capacitors in this sense, we're only talking about the asymmetric field that is created, and that field itself will generate thrust and has been the subject of an awful lot of research. Now, to make one actually is really stupidly easy. You need something to create one large plate, and because what we're going to do with it to demonstrate that the thrust is happening, we're going to use a coffee can. We're going to use a coffee can because it's got a great big metal covering here and then some nice cardboard here that's thick enough to resist the voltages that we're going to put through it. And then all we're going to do is take a wire and put that wire around it. So we've got a thin metal here and a great big one here, and if we put a voltage across that, what we're going to do is create an asymmetric capacitor in the sense that we're talking about. What I've got is an iPad, and that's my sound source. It's playing some music into this Yamaha amplifier, and the amplifier is being then fed into this bog standard ignition coil. Now the ignition coil is really easy to identify. There's a plus and a minus marked on it, and obviously that's the outputs from the amplifier. And then that's the high tension lead, and then there's the earth return. Now, even though it's coming through the amplifier, it's actually outputting about a volt or so it's not massive that's going into here. This is a 2000 to 1 step-up ratio, so it's round about 2 kilovolts, 1.5 kilovolts, something like that coming out. So in high voltage terms, that's actually relatively a low voltage that's been fed out. Anyway, that's that. Let's turn it on and listen. Okay, so granted, that sound quality was, well, it was as rough as two dogs. And if you've seen two dogs fighting over a bone, that's rough. But something in there was making the air move and vibrate, which is why we heard the sound. Now, there are a couple of things you might think about. One of them might be, well, heat. The other one might be ion movement. But it was only about 1.5, 2000 volts, remember, so not a particularly high voltage in high voltage terms, but it still might have been ion wind that was responsible for that. That's not an unreasonable supposition. So, I got myself a bit of paper and a pencil. Now this pencil's a 9B pencil, so it's very high in graphite content. What you do is just draw an asymmetric capacitor. It's quite an easy thing to do. We've got a centre section there, and we've got a cup. Now because the voltage is so low in inverted commas, and the breakdown voltage of air is something like a kilovolt per millimetre or something, or kilovolt per centimetre, if we put that further away than 2 centimetres, then we're not going to get arcing, but we are going to have a capacitive structure. Now if I'm not talking total BS, what will happen when we connect that to a high voltage supply is that a capacitive field will be set up, and it'll be set up perpendicular to the paper, so it'll come out in that direction. Now if we put a piece of metal foil over there, what that will do is induce an opposite charge, and of course because it's now an opposite charge, what we should get is a force of attraction and repulsion on that piece of paper, or rather on that piece of metal foil. Now I think anything will do that, so if you put a bit of plastic on there and a bit of aluminium foil, that'll do it just Jim dandy. But of course you find these things being sold all over the place because aluminized mylar foil is what we use as food packaging. The layer of aluminium between the two plastic films creates an air barrier keeping everything nice and fresh, like a crisp packet. So if we cut a square from a crisp packet, we'll have exactly what we want. Now if we connect it up to our high voltage supply, and high voltage on that side, put our bit of plastic over there, and I'm going to put this over because I don't really fancy getting a shock. Now to continue that one stage further, what I have is this. It's a bit of window film, and we're going to do the same thing. Just lay it on the top there and start the music. Now, based on those two experiments, I would argue that there wasn't enough voltage to strip the electrons from the air and create an ion wind. But what was happening was that we were creating an electrostatic field that was influencing, in the second case, the metal plate that we had over it. But in the first place, when we were using the coffee can, it was influencing the behavior of the air, creating a repulsion to one side and a wave of attraction and repulsion passing through the air, which we heard as sound. Now, it is an area of great contention with a lot of argument about how it's actually working and no real conclusion. But if it's working because it's a field that's creating the propulsion, then of course it's very interesting in things like space travel, which is exactly why NASA have been looking into it and why they had that patent. Anyway, if nothing else, it's an interesting effect, and it would certainly make a great way of making a flat panel electrostatic speaker. But I hope you enjoyed the video, and thank you very much for watching.